Hi everyone! Today I'm going to present our work about the perceptually uniform construction of illustrative textures. I'm sure most of you know illustrative techniques such as stippling and hatching. There, primitives like dots and lines are used to mimic tones and shadows for artistic drawings or illustrations. But what if we want to use these techniques to encode data? Often, data is encoded on surfaces using color maps. However, sometimes we might want to use grayscale images, or we could use illustrative techniques to encode an additional attribute. In our work, we investigate the perception of illustrative textures, or more specifically, stippling, hatching, and triangles. Now, how do we map data to textures? In prior works, the mapping was chosen without empirical justification. Given these sequences, which one would you choose? Our goal is to find sequences that allow the viewers to easily interpret the texture level as the correct data value. So, how did we do that? First, we generated the stimuli spaces. Then, we conducted a crowdsourced study in which the participants rated the differences between texture levels. Then we visualized the perceptual spaces by applying multidimensional scaling. To get some practical output, we reparameterized the perceptual spaces. With this reparameterization, we can map from perceptual to density space and vice versa. Finally, we could create approximately perceptually uniform texture levels with our reparameterizations. So, in the first step, we created the stimuli. The textures on this slide show a subset of the stimuli we used in the studies. For stippling and triangles, we sampled the density spaces in 0.05 step increments. To keep the number of comparisons feasible, we could not sample the cross-hatching space as densely. The space is two-dimensional and we chose step sizes of 0.2 for vertical and horizontal hatches. The textures were overlaid to generate the 2D space. Next, we conducted a crowdsourced study with 60 participants, 20 for each texture type. The participants compared all possible texture pairs and rated their differences. We used a very open question formulation to avoid bias. We just asked the participants to judge the similarity of the images on a scale from 1, very similar, to 9, very different. Then we analyzed the results with multidimensional scaling. Multidimensional scaling, or MDS for short, takes a symmetric matrix of similarity ratings as input. It then finds a lower dimensional representation of the data. The pairwise distances are preserved as accurately as possible. Here you can see the perceptual spaces of our illustrative textures. We generated our texture sequences for stippling and triangles by varying one parameter only, the density. We expected to also find one-dimensional perceptual spaces. However, the results could not be described by one dimension. The perceptual spaces seem to be 1D manifolds in two-dimensional space. The results for cross-hatching are, as expected, even more complicated. We can see one cluster of cross-hatched textures at the top and the one-dimensional hatching textures at the bottom. Interestingly, if we only take the 1D hatched textures into account, we find that they also seem to follow the same distribution as the stippled and triangle textures. In the left image, you can see that horizontally and vertically hatched textures align very well. The image to the right shows that stippling, one-dimensional hatching, and triangles all roughly follow the same distribution. So, what did we learn so far from our studies? Our constraint-free study approach revealed the need for 2D descriptions. The perceptual spaces were not sufficiently described by one dimension. Stippling, one-dimensional hatching, and triangles can be described by one-dimensional manifolds in two-dimensional space. A downside of multidimensional scaling is that it does not reveal the meaning of the dimensions of the perceptual space. So, in future work, the relationship between physical and perceptual dimensions needs to be explored further. Now that we've got our perceptual spaces, we want to use them to create better, more intuitive visualizations. We therefore want to use perceptually uniform texture levels. To generate these, we need evenly distributed points in perceptual space and a function that maps from perceptual to density space. We fitted curves to our sample spaces by using a Sawicki-Golay filter. With these curves, perceptually uniform texture levels can be derived. Note, however, because our space is not one-dimensional, the levels are only locally perceptually uniform. What do I mean by this? The perceived distance from one texture level to the next is, by construction, always equal in perceptual space. However, because of the curvature of the manifolds, the distance from one texture to a texture several levels further down is different for different textures. Additionally, we found that our reparameterizations are well described by sigmoid functions, as you can see on this slide. Here we have the perceptual values on the y-axis, the density on the x-axis. The reparameterizations are shown in red and the sigmoids in yellow. With our general derived sigmoid functions, it is possible to map from density space to perceptual space. With the inverse function, a mapping from perceptual to density space is possible. Note, I use sigmoid as S-shaped curve. I do not refer to the logistic function. In contrast to the logistic function, our derived function has the benefit of reaching its bounds. The logistic function does so only in infinity. So, we recommend using our mappings to generate perceptually uniform texture levels for visualizations. However, there are some limitations. The samplings on the extreme ends should be refined in follow-up experiments because they were quite coarse in perceptual space. You can see this in the picture. There, the distance between the black and the almost black and the white and the almost white texture is very large. And because our structure is a 1D manifold in 2D space, the levels are only locally perceptually uniform. Now, on to some practical examples. With our reparameterizations, we generated these continuous textures that are approximately perceptually uniform. Here you can see data mapped with illustrative textures. The first two examples are for discrete data values. The first image shows a carotid artery model and the second a molecular model. The last example has continuous data on a brain model. So, to come back to our original question, how should we choose a mapping? Well, we recommend using the last mapping with 1D hatching and our perceptually uniform levels. The perception of cross-hatching is too complicated and therefore not as easily perceived as the correct data values. So, to conclude, what are the main takeaways from our work? We found that 2 dimensions are necessary to describe the perceptual spaces of illustrative textures. Stippling, 1D hatching, and triangles can be described by 1D manifolds in 2D space. These manifolds can be reparameterized and used to generate perceptually uniform texture levels. In turn, the reparameterizations are well approximated by sigmoid functions that map from density to perceptual space. Finally, we advise against using cross-hatching for encoding one-dimensional data. One-dimensional hatching is more easily mapped to data in an intuitive way. Thank you for listening.